Welcome to the listeners of TALRadio English. This is CXO Showtime with your host Akshay. Today we are going to talk about a unique organization, SETI, Search for Extraterrestrial Intelligence. SETI has unified several research disciplines by their relevance to the search and understanding of life beyond Earth. Today, the Institute has approximately 100 scientists as well as specialists in administration, education, and outreach. Our guest today, Bill Diamond, is President and CEO of SETI Institute. He has worked predominantly in applied technologies with over 20 years of experience in photonics and optical communications. His corporate background spans the spectrum from venture-backed startups to Fortune 100 multinationals, with responsibilities ranging from R&D, engineering, and operations to sales, marketing, product management, and CEO positions. Bill has held CEO positions at Wave Splitter Technologies, Dense Light Semiconductor, and X-Radia Inc., now part of Zeiss. He also served as a president of US operations for the Swiss technology company Comet AG. He is a past member of advisory board for the McDonough School of Business Administration at Georgetown and is a current member of the Optical Society of America and the International Astronomical Congress. Bill, thank you for the time. Great to have you with us.
Pleasure to be here. Thanks very much.
How and why the organization started, Bill?
The organization started actually in 1984. It started essentially because the resources available to those doing SETI research, in other words, using radio telescopes primarily at that time to look for signs of technology beyond our solar system as proxies for life and intelligence beyond Earth, was not robustly funded by federal agencies such as NASA or the National Science Foundation. And also, while some of the original founders were working at the NASA Ames Research Center in Mountain View, where we are still headquartered, there was a feeling that there was an opportunity to start a research institution devoted to this field broadly, not just in terms of SETI looking for signs of technology and intelligence, but also the broader field of astrobiology, which is the study of life in the universe. So even life in its most basic forms, but not life here on Earth. And to bring together researchers pursuing those fields and those endeavors in an environment where they could come together in an organization and have an overhead rate, basically, an indirect cost rate, as we call it, that would be lower than traditional entities like universities and large-scale research institutions, therefore offering, perhaps a more competitive environment for scientists to submit proposals to funding agencies and be funded for their work. So that's kind of the genesis of the Institute. But the endeavor that the Institute was founded on dates back to about 1960 and actually 1959, based on a paper that came from a couple of Harvard astronomers speculating the prospect of using radio technology, specifically radio telescopes, to look for signs of or radio frequency signals coming from beyond our solar system as a means of looking for intelligent life beyond Earth.
And how is NASA associated?
NASA is, of course, a federal agency of the United States government, and NASA, interestingly enough, the way NASA is structured, by way of quick background, is NASA has four so-called directorates, four primary areas of activity. One directorate is that perhaps the public is most familiar with is Human Exploration Operations, or so-called HEO, and that's the part of NASA that puts astronauts in space, whether on the shuttle or to the space station or to the moon, et cetera. They also have what's called the Science Mission Directorate. The Science Mission Directorate, as the name implies, is all about research, and pretty much every unmanned spacecraft that NASA has ever launched, Cassini and New Horizons, the Kepler telescope, Hubble, et cetera, have all been under the direction of the Science Mission Directorate. They also have the Aeronautics Directorate, which is more about flight technology in our own Earth system, so things like supersonic flight and engine technology, wing design, and so forth. And Then they also have the Space Technology Mission Directorate, whose job is to sort of help develop the technologies that support the other three. The Science Mission Directorate has three science questions. Basically, there are three questions which drive all research at NASA. The first one is, how does the universe work? And the second one is, how did we get here? How did life emerge on this planet? And how did humans ultimately emerge from that life? And then the third question is, are we alone? The Institute, while being an independent entity from NASA, we're a separate so-called 501c3 nonprofit research institution. Much of the funding for the work we do comes from NASA, where our scientists, like scientists in academic institutions and other research entities, write proposals to NASA, where NASA does what we call solicitations. They put a call out to the research community to say, we're interested in research proposals along these lines or to investigate this question. And so our scientists will submit proposals to NASA to fund their research. And about 85% of the funding that supports the Institute comes from federal agencies, and about 85% of that 85% is NASA. So most of the funding for the work that we do at the Institute comes from NASA. Other funding comes from National Science Foundation, National Institutes of Health, U.S. Department of Energy, U.S. Geological Survey, organization called UCAR, and others, but again, dominated by NASA. Interestingly, federal funds are not used to fund our namesake endeavor of SETI research, where we use radio telescopes and now also optical telescopes to look for signs of life beyond Earth, signs of life in the form of signs of technology. So there is not federal funding available for that endeavor. So those efforts are funded by private philanthropy, private individuals, and foundations and organizations interested in supporting that work.
What is extraterrestrial intelligence, and how are we defining it?
That's a great question, and I would say in many respects, SETI is somewhat of a misnomer, because from a technological standpoint, we are not looking for signs of intelligence, because intelligence isn't necessarily something that has an obvious fingerprint or signal that one can look for, but rather we're looking for signs of technology. We're looking for, I guess, civilizations that have advanced to the point where they are doing as we started to do about 100 years ago, taking advantage of the electromagnetic spectrum, inventing things like radio and lasers and other things which can operate across the vast distances of interstellar space and even intergalactic space and be detected from a great distance. So the underlying hypothesis is that if the universe is full of planets, which we now know that it is, and if a large number of those planets are habitable worlds, which we now know that they are, doesn't mean that life has evolved, but it means that there are billions and billions of planetary systems where life has the potential to emerge and evolve. So if that's the case, then the assumption also is, or the assertion is, that not only here on Earth, but elsewhere in the universe, life has had the opportunity to evolve to the point of advanced species that ultimately are able to develop technologies similar to our own that we can detect at a great distance. So that's what SETI is. SETI is basically an effort to look for signs of technology that manifest themselves across distances that, other things to look for are not possible, like the lights that we have on our planet. When it's dark out at night and all our cities are lit up, that kind of light can't be detected very far away at all. But radio waves can, laser pulses can. And so this endeavor is really all about looking for signs of technology that come from beyond our solar system that would, quite frankly, be sort of irrefutably indicative of life and intelligence beyond Earth. So it's the search for extraterrestrial technology as a proxy for both life and intelligence.
So SETI's work mostly revolves on all astrophysics or astrobiology, or there are other streams of education that are getting involved into the overall experiment here?
Yes, well, almost all the branches of the natural sciences are represented by researchers at the Institute. They come from 23 distinct backgrounds that include things like geology, microbiology, biology, chemistry, physics, astrophysics, astronomy, planetary science, instrumentation and technology development, data analytics, machine learning, artificial intelligence, et cetera. So it's a vast array of fields. And among other things, one of the things that we investigate or study quite closely is what we call the coevolution of life and environment. So life and environment are inextricably linked together. Life on this planet has influenced the environment that is around us from the very beginning, and equally, our environment continues to this day to influence and impact life. And so these two things co-evolve over, millennia and eons, and impact one another. So, it's impossible to study something like life beyond Earth without also understanding notions of habitability, notions of environment, notions of climate, notions of basically all the interconnected natural phenomena that gave rise ultimately to humans here on Earth and to life here on Earth, and presumably would be involved equally elsewhere. So we have people who our science is essentially divided into 6 research topics. So astronomy and astrophysics, climate and biogeoscience, as we call it, exoplanets, the study of planets beyond Earth, planetary exploration, which is developing the tools and technologies to look for life in our own solar system, astrobiology, which broadly means the study of life in the universe, but the astrobiologists at the Institute are typically studying life here on Earth in extreme environments to understand the envelope of conditions under which life can exist. And then lastly, SETI, using radio telescopes and optical telescopes to look for signs of technology at great distances. So those are the different sciences within the Institute.
And how does the collaboration of the scientists come into play? Do you reach out, or the scientists reach out to you based on the work that you're doing? Do you have any collaborations with institutes who are working in and around the same space?
Absolutely, yes. So typically when a scientist submits a proposal to NASA or some other federal agency, for example, the scientist who's coming up with the idea initially and is going to put together very often a team. It could be just 2 or 3 people. It could be a dozen or more people. But that individual is called the so-called principal investigator. And so if a principal investigator is here at the Institute, they're putting together a research team to work on a particular project. Many of these teams are interdisciplinary, so they might include chemists, a physicist, an astronomer, a geologist, a biologist, et cetera. So the teams are often by necessity multidisciplinary, depending on the nature of the work. And so the scientist, the so-called principal investigator, will generally, of course, look to his or her colleagues within the Institute to see if the relevant expertise they're looking for is here, resident at the Institute. And equally, they will go to outside institutions. Of course, all of these people went to graduate school, got PhDs, may have started their careers in different places. So there's quite a network of scientists who know one another, and they'll tap into their network and or look for people they don't yet know in certain fields. And those individuals might be from academic institutions, MIT, Stanford, Berkeley, Georgia Tech, University of Arizona, University of Tennessee, et cetera. Or they might be from other research institutes, notably the Planetary Science Institute for one, or the Southwest Research Institute. So generally, collaborations are a big part of our work, and also that includes international collaborations in different countries, particularly when our scientists, as they often do, are going on what we call field expeditions to remote places to study phenomena there, and they'll be collaborating with local universities or research centers to do that work. And equally, principal investigators may be from another organization or institute who will tap into the scientists at the institute to have them join their team. So it works both ways. We have projects in which our scientists are the principal investigators, and then other projects in which our scientists are so-called co-investigators, are part of a larger team that's centered elsewhere.
You got a very interesting data point out there about collaborating with a lot of organizations globally. Does that also mean that we have a lot of places on our Earth which can provide us more information about understanding extraterrestrial intelligence?
Yes, yeah, absolutely. I mean, we all recognize, I think, that we have one research laboratory, one example that we know of where life has evolved on a planetary system, and that's here on Earth. So, the Earth is a massive laboratory for us in which we are studying both the wide range of species on the planet, so-called biodiversity of the planet, how life begins and under what conditions, how it happens, how it evolves, what different environments, how those impact and influence life, and the ability of life to exist in environments we call so-called extreme environments under frozen lakes in Antarctica, or in the driest place on Earth in the Atacama Desert in Chile. And so we've learned over the years of study that the conditions under which life can exist are much wider than we would have thought, say, 20 years ago. And even geological phenomena such as volcanoes and earthquakes, wind and weather. I mean, all of these things play a role in the distribution and diversity of life. And so studying Earth as a system, studying individual places on Earth that might teach us or have something analogous to other places in say our solar system, like Mars. There are places on Earth at very high altitudes where the air is thin and the temperature is very cold that mimic conditions on early Mars, and so forth. So we go to places all over the planet to study different phenomena that we feel are likely to exist on other worlds as well, and again understand notions of habitability, habitable environments, coevolution of life and environment, and so on. And of course, in the process of doing this, and this is why we often make reference to this when we talk about SETI as an endeavor, or astrobiology. In many respects, this is about holding a mirror up to ourselves. We're learning a lot about ourselves as a species. We're learning a lot about other life forms on this planet. We're learning a lot about the planet itself as a system, in the process of studying, how to and where to look for life beyond Earth. So this is a laboratory we take advantage of extensively.
Carl Sagan Center for Research. That's for research. That is more prominently around collaborating in and around most on the optical side of research activities from a telescopic standpoint. Is that what?
No, the Carl Sagan Center, it's named in honor of Carl Sagan, who, of course, popularized a lot of interest in cosmology. But his interests were broader than that. They included earth science and climate and things like climate change and human behavior and so forth. So he was, kind of a man for all seasons in many respects. But and he was on the board of trustees at the Institute in the final years of his life. So we've had a long connection to Carl Sagan. So the research center is named in his honor, but the research center, there's basically three centers at the Institute. There's the Center for Research, which we call the Carl Sagan Center for Research. And there's the Center for Education, which runs education programs, primarily STEM education programs. And then there is the Center for Outreach, which is all about public engagement and interaction, and communications with the general public. So the Carl Sagan Center is where all of our research scientists reside, if you will, organizationally, regardless of what kind of science they're doing. They're all organized under the Carl Sagan Center. And then the education and outreach centers have their own teams.
There are a lot of current projects that you're working on. We would be enlightened to hear more about the current projects that SETI is built from your end.
Sure. Well, I can start with a SETI project, since that's, again, a namesake endeavor. One of the most interesting projects we have going on at the moment in SETI technology or SETI research is a project in partnership with the National Radio Astronomy Observatory called NRAO, which runs the massive radio telescope observatories in the United States. It's a federal organization. One of the telescope systems that they operate is called the Very Large Array, which is based in Socorro, New Mexico, flat sort of desert area, quite remote. And this is it's an aptly named telescope, Very Large Array, because it is an array of multiple radio telescopes, each one of which is quite large. Each one is about the size of a 10-story building. There's 27 of them arranged on a pair of railroad tracks that mark out the shape of the letter Y and extend over 27 miles of this desert region in New Mexico. And it is the most productive radio telescope on the planet. In fact, it is among the most productive telescopes of any kind, radio and optical, in terms of the amount of research and the amount of papers that are published based on research done on the Very Large Array. It's one of the most sensitive radio telescopes on Earth as well, although there are two newer radio telescope arrays in the Southern Hemisphere that will ultimately be more sensitive. But the Very Large Array is a very iconic telescope. If you're familiar with the movie Contact with Jodie Foster and Matthew McConaughey, the famous movie poster, the famous movie poster for that movie has in the background the dishes of the Very Large Array, which at that time and up till very recently had actually never been used for SETI before. They've been used for other radio astronomy observations. But we've partnered with NRAO and the VLA to put a new fiber optic back end on that entire telescope array, where each radio telescope dish now has two fiber pipes going back to the computer center. One of them feeds the computers of NRAO, and the other one feeds the computers now owned by the SETI Institute, where we are capturing what's called the entire field of view of that telescope. So very often that telescope is doing the same thing you do, for example, with a pair of binoculars. You're looking through the binoculars and you're looking, at a bird or a butterfly or a building, but something specific. But all around that object is a bigger field of view that you can also see through your binoculars. Similarly, with the radio telescope, the scientists getting time on that instrument are usually looking at some point phenomena in space, a pulsar, for example, or a magnetar, some kind of phenomena. And yet the telescope is capturing all this other information. That's what we're interested in. So we launched a project called Cosmic, which will operate in what we call commensal observation mode, meaning sort of piggyback. Whatever they're pointing at, we'll be pointing at the same thing and basically capturing the field of view to look for SETI signals of different types, and likely we'll have other astronomical, astrophysical phenomena that we capture in that field of view that will be, available for study and research. So it's a massive program. It's probably, I think, the most significant SETI endeavor ever undertaken, because it's 24 hours a day, 7 days a week, and it's, again, with the most sensitive radio telescope available in the world. So we're very excited about that project. And as it happens, the VLA is just starting an 18-month project, which is called the All Sky Survey, which is exactly the kind of thing we'd want to do with such an instrument for SETI purposes, is survey the whole sky, just look at every segment of the sky. And they are doing that for their own purposes. We're going along for the ride, and we expect there's going to be, lots of exciting knowledge and perhaps interesting new discoveries made as a result of that program. So that's one of the projects I think that we're quite excited about. Another program that we're involved in involves the James Webb Space Telescope, which I'm sure you're aware, launched at the beginning of last year and unfurled over the ensuing months, and is already now delivering spectacular images from space. So one of the unique capabilities of that telescope is the ability of the telescope to actually look at the thin veil of atmospheres around exoplanets, meaning planets outside of our solar system orbiting distant stars or distant suns, if you will. And it has the ability to do what we call infrared spectroscopy, which is a method of understanding based on looking at the light that passes through the atmosphere, what the atmosphere is made of, the composition of that atmosphere. Does it have oxygen, nitrogen, carbon dioxide, methane, other things? And the purpose of which is to look for what we call biosignatures or potential biosignatures. In other words, atmospheric compositions that would be difficult to explain in the absence of life or some biological system or mechanism that is maintaining a particular atmospheric composition. So that's very exciting because this is the first time really that NASA technology has been able to look beyond our solar system for possible indications of life. So we're very excited about that project. We have another project, NASA related again, in which a spacecraft called OSIRIS-REx was sent a few years ago to an asteroid called Bennu, and it orbited that asteroid for more than a year, doing detailed mapping of it. And then it went down very close to the surface, and it scooped up some material from the surface of that asteroid and put that material into a little clamshell, kind of like a backpack for the spacecraft. And that spacecraft is now on its way back to Earth with that backpack. And in September of this year, that backpack will be ejected from the spacecraft and land in the deserts of Utah, containing material from this asteroid. And this asteroid, like many asteroids, contains material that dates back to the very beginnings of our solar system. So we expect to learn a lot about the composition of that material and what kind of elements and molecules, minerals, and potentially even organic or pre-organic compounds might be in that material. So that's a very exciting project. One of our scientists is on the team awaiting that sample return mission. So that's another project of interest. We have another scientist who works in a research lab, a chemistry lab that's actually based at NASA Ames, and she looks at for example, how we might break down urine into its component parts that allow us to have both water and rocket fuel. So these kinds of technologies could be important, for example, for habitats on places like Mars or the Moon, where you have limited resources available to make things like fuel and produce things like water. So lots of interesting work of that type as well. So anyway, that hopefully provides you with the kind of a sample of some of the kinds of work that's going on.
Well, Bill, with that hope of getting some more information back to us, let's take a break here as we come to the end of our episode. And we look forward to have you again for our second episode next week. Thank you, Bill, for staying with us. We'll catch up with you again next week. Thank you.